And hello, welcome back. Welcome back to this video series. Okay, we are discussing laminar flow boundary layers, and we just went through some extensive tensor multiplication. Let me check the volume. Okay, that's good. We just went through some extensive tensor multiplication. We took the divergence of a tensor. Rank 2 tensor, meaning to say it has I and j indices, meaning it's 2D basically, a 2D tensor, which can look like a 2D matrix. We did a Laplacian of that. And basically we find that when we take this dot product with the tensor, we're supposed to get back a vector, so we kind of reduce the order of this tensor vector thingy by 1. Okay, so great. Now what's next? Okay, in our boundary layer equations, we try to simplify this incompressible Navier Stokes into 2D. Okay, so let's just write this down. Okay. I'm going to just put it explicitly in x, y, and z velocity. No longer am I going to put it in vector form. So it's at least clearer what's going on. Okay, so what I'm going to do, I'm going to put all of these things down. This Laplacian term down. Okay. So this is u vector ur, right? Okay, so let's capture some of this. I'm going to take this first row here, okay, which is right over here, so that you can see what's going on. And of course, next I will take the first element as well. Okay, so this is the Laplacian term. Oops, so sorry. Let's get the right one. Yeah. And now we can replace the Laplacian term as well. Okay, let me try again. Yep, this is the one. And let's do the Laplacian term as well. Okay, so I have all of this here. Now of course we want to replace our u1, u2, and u3 by x, y, and z, or u, v, and w. It's a lot more simple. Okay, so this is what we have. Of course, I want to change all of this into del squared. Okay, and u1, u2, and u3 can be replaced. So u2 will be the y velocity, which is v. u1 will be the x velocity, which is u. u3 will be the z velocity, which is w. Okay, so let's get rid of, so I'm just replacing some of these what do you call that, some of these terms here. Okay, as you can see, I'm actually just replacing the indices. Alright, and then I'm also, of course, getting rid of some of these what do you call it? I'm getting rid of this fractions and everything. Okay, so I'm just tidying up the equation just to make it look nicer. And then once we are done, we'll just do the same for the y and z velocity. Alright, so right, so this is our Laplacian term. Okay, and then Lastly, we'll just deal with the gravity bit. So this is the x momentum equation. So it's just gx, okay, and I'll just do fraction like so. P. So this is the x pressure gradient. Okay. Alright, so now it looks a little nicer. Okay, I'll just repeat for y and z. So I'll just paste it first, and let's do it for y, the y part. So this is what we pasted down. I'm just going to change some of the velocities on the inside. Okay. Of course, if you want to replace this by the substantial derivative, you can. It's going to collapse it and make it a lot neater. But when you want to start cancelling terms, it's going to be a little bit more annoying. Okay, so we have the substantial derivative here. We have the same Laplacian term here, so it's going to be exactly the same. Okay, let's check. So the Laplacian term will be all u's. So I kind of here it needs to be a u. Okay, let's change this to a u, and the Laplacian term will operate on the velocity of interest, of course. So in the second equation is the y momentum equation. It's going to be a v, and of course we'll change the pressure gradients to y coordinates as well. So partial p partial y, gy. So all of these actually operate on the v velocity. Okay, and the substantial derivative also operates on the v velocity. Last but not least, of course, we'll do the z. We'll do the z equation. So I will start changing terms. As you can see, I'm working from the right hand side. And then I'll deal with the Laplacian term. Last but not least, I'll just deal with the substantial derivative term. So you can see I'm slowly changing some of the terms here. So 1, 2, 3, all of these are w velocities. So here inside should all be w as well. And the substantial derivative should operate on the z velocity. Okay, now for 2D, what do we do? Okay, w equals to 0 everywhere. That's the assumption that we are making, simplifying assumption that we are making on what do you call that? 2D boundary layer equations. So in effect, the z velocity thing the whole thing can just disappear, because the w equals 0, all the derivatives are 0. So everywhere and at all times, w equals to 0. Okay, so the derivative with x, y, and z all are 0. The second derivative all are 0. And gz also should be 0. Okay, that's the other assumption we are going to make. Okay, so all in all, the pressure gradient with respect to z is 0. Nothing too interesting there. So we can also eliminate. Okay, we eliminate the z terms from the x and y momentum balance. Okay, so this w should disappear as well. What else? Yeah, that looks like the only time w is over there. Okay, so let's get rid of the w terms in the substantial derivative. So that's 1, and yeah, that's 2. Let's see whether it looks right. What else should we cancel? Anything. The next assumption we make, okay, So we got rid of our w. We need to assume that anything with respect to z, okay, there is no spatial variation with respect to z. Okay, no spatial variation in u and v. In u and v. So that's truly a 2D problem. So all of this should be 0 as well. So this del by del z should be 0. Okay, so the second derivative should also drop out. Okay, and here we'll drop both of them out. Okay, so now we basically have a 2D Navier Stokes. Okay, we have a 2D Navier Stokes. And what do we do next? Okay, so this is the part where we get from a 2D Navier Stokes to a boundary layer equation, because not all of these terms are so-called important. Some of these terms you can kind of ignore, some of these terms you cannot. Okay, so for example, okay, in a boundary layer equation, where's my doodle pad? Okay, so let's see. I have to clear the blackboard here, save it. Let's use green today. Okay. Okay, so in the boundary layer equation, what we have is, of course, the flat plate where the velocity here equals to 0. So the velocity here equals to 0, and of course we'll have this sort of boundary layer. Okay, of course the boundary layer thickness at wherever at the x equals to L. Alright, so depending how far you go into the plate, this boundary layer thickness delta will change. Of course, you have the u infinity. Alright, so, and of course in the free stream, this is the free stream, right? In the free stream, the x component of velocity, u equals to u infinity, and then the y component of the velocity equals to 0. Okay, of course when you start to encounter the boundary layer, the u here is actually less than, the x velocity here is less than u infinity. Alright, the x velocity here is less than u infinity. So the fluid must go somewhere. So if the fluid is being stopped near the boundary layer, it has to have some y velocity. Okay, it has to have some y velocity. So how big is this y velocity? Okay, how big is this y velocity compared to u? All right, so u, we can say u is on the order of u infinity. So when I write this O notation here, it represents order of magnitude. I think let's see. Okay, let's see whether this works on LaTeX. You can use some programs like MathCal to actually get your order of magnitude. Okay. Order of magnitude. Okay, so I hope I'm getting the right one. Yeah, this is what the O thingy looks like. I use MathCal. Okay, it's a standard LaTeX package. So what do we have here? Okay, so I don't know how to write that O properly, but I'm just saying here, this is the order of magnitude of u infinity. And of course, we can say on average, wherever you go, u is going to be much greater than v. Okay, this is the kind of intuition we get because u infinity is very big and we start with 0v velocity, and the only way we are going to get y velocity or the v velocity is only through the slowing down of this what do you call that, boundary layer. Okay, so because the fluid slows down, it has to go somewhere, right? So if we take a look at the continuity equation, which I kind of forgot to yeah, if you take a look at the continuity equation, let's see. Do we have a continuity equation? Yeah, this is the continuity equation. Alright, I forgot to include that. But I'm not going to simplify. Okay, basically this continuity equation is fraction partial by partial x. This is the divergence term. Okay. Partial y v plus and of course you have the z velocity as well. Which is w. All of this will be equal to 0. Okay, all of this will be equal to 0. And apparently I had a syntax error somewhere. Okay. I spelled partial wrongly. It's partial derivative. Alright, let's see whether this works. Okay. And of course the second one I want to get rid of the w because w is 0 everywhere. So as you actually slow down your u velocity based on a continuity equation, yeah, you slow down your u velocity based on continuity equation. This term is going to be a negative term. Okay, so as let's say you stand here, you take a look along the whole boundary layer, you realize that your u velocity is going to slow down. So okay, del u del x is going to be less than 0. So del u del y, or del v del y, is going to have to be more than 0. So there's a positive gradient. When you go from here, you increase your y velocity, your y coordinate, the v velocity is going to increase. Okay, so this is just continuity equation. The fluid has to go somewhere. So if it's going here at the free stream velocity, and it meets this boundary layer, it's just going to get redirected upwards. The flow is getting redirected upwards. Okay, that's what the continuity equation is. Okay, that's the only way that you're going to gain any kind of y velocity. But on average, the u is greater than v. The x velocity is going to be greater than the y velocity. But by how much? Okay, and what kind of terms can we cancel from these equations based on what we were saying just now? Some terms, of course, are going to be bigger than other terms. So is there a way to properly and systematically compare these orders of magnitude? And answer is yes. And the thing that we need to do for order of magnitude comparison is called scaling. Okay, it's called scaling. So what is scaling? Basically, okay, let's say we have u. We're saying, right, u is on the order of magnitude of the free stream velocity, right? So when we want to do scaling, all right, we want to replace, how do you say? Okay, we want to replace everything by dimensionless variables. So that's a very big term, very big thing we like to say in fluid mechanics. Okay, so let's say u is on the order of magnitude of this free stream velocity, right? U is on the order of magnitude of this free stream velocity. Okay, so let's say we could divide these two out, and I say this new quantity is on the order of magnitude of 1. Okay, this is actually a dimensionless velocity, u prime. Correct. So this is on the order of magnitude of 1 because I said that earlier that this u velocity is on the same order of magnitude as this u infinity, which is the free stream velocity. So to make it easier to compare, I want to change the variables in this equation. I want to change all the variables in these equations to some sort of dimensionless variables, right? Why? Because when I compare, let's say u prime, and this is supposed to be order of magnitude 1, and somehow I change all my variables such that I do a similar kind of a process. I do a similar non-dimensionalization for v. So I can say the v prime is of course v divided by some characteristic velocity scale for the y velocity. I will say this is on the order of magnitude of 1. So now when it's very intuitive in a sense that when we compare u prime and v prime, we can say that they are all on the same order of magnitude. Okay, they're all on the same order of magnitude. And what happens? Okay, somehow you get all of these terms factorized out. Okay, somehow you get all of these terms factorized out, and then you can do comparison there. Okay, systematically looking at the equations rather than you check for all of these. Okay, you have to think of, okay, u is how much, v is how much, and why not you just change everything into these dimensionless variables and you pull out all of these so-called order of magnitude factors. For example, u is on the order of magnitude of this free stream velocity, v is on some other order of magnitude, we have not discussed that yet. But once we pull out all these terms, we can then do some comparison there. So if you're still confused, don't worry. I'm going to demonstrate a little bit of this. Okay. So one thing we want to do is to change, of course, our u velocity. All right. So the u velocity here, okay, we define. Again, I'm going to use the same thing, right? So the u prime or u star, I'm going to call it u star, equals to u divided by the free stream velocity, u infinity. Okay, all right, this is one of the most common ways, right? Okay, we have u star equals to u over u infinity. So what do? We substitute the expression for u. We substitute the expression for u, which is u equals to u infinity, u star, and then we just substitute all of this back into the equation here. Okay, cool. Right, so let's start with the simple stuff. We already kind of did this order of magnitude comparison for the x velocity. Now let's do an order of magnitude comparison for x. Okay, so let's do x star equals to fraction of x over L. Remember we were saying for a flat plate, right? A flat plate, okay, at length L, there will be some boundary layer thickness delta. And what's this boundary layer thickness? Again, I want to re-emphasize that the u velocity equals to 0.99 u infinity. That's a very common boundary layer thickness. Okay, so wherever the x velocity crosses this 0.99 times of the free stream velocity here, okay, then it will be counted as, okay, you're inside the boundary layer. All right, so what is the characteristic length scale of x? Okay, so the characteristic length scale of x will be equals to L. Okay, L is how far into the boundary layer you're talking about. And now because we have this we have this boundary layer thickness delta. This is called momentum boundary layer thickness. Why is it called momentum boundary layer thickness? Because this deals with velocity. Okay, this deals with the velocity, and of course mass times velocity is momentum, right? So anytime the momentum drops below 0.99 times of the free stream momentum, because you can of course just mu both sides, multiply both sides by the mass or density or whatever you have, it becomes a momentum boundary layer. Okay, so this delta is a very good length scale for y. Alright, it's a very good length scale for y. So x has a length scale of L, okay, and the y coordinates of interest within the boundary layer have a length scale of delta momentum. Okay, so let's express this. Y star equals the fraction y over delta. Then I'm going to use the subscript p to denote a momentum boundary layer. Of course, there are other kinds of boundary layers as well. If you do more heat transfer, you'll realize there's a thermal boundary layer as well. But for purposes of this discussion, I'm skipping that. But I just want to make it clear that this is a momentum boundary layer, delta p. Okay, so I'll stop for now. I'll continue more of this in the next video. So thanks for watching. See you guys again.